Hello, how are you doing? How are you doing? Gotta make sure my okay. Good. Okay, so let's check out the lab. Let me adjust my volume here because that might be a little loud. Sorry about that. So we're gonna do multiplication and division today. Okay, we'll start in a couple minutes, okay? Let me open my simulator. Go ahead and access your editor and your simulator.
Hello,
Hi, how are you doing?
I'm doing good, and you?
Good. Sierra,
Yes.
at the end of the session, if you want to stick around for a few minutes, I want to talk to you privately a little bit about your STEM situation, okay?
Okay.
All right.
I can do.
All right. I guess that's what we have right now, 11 people. Oh, maybe people will join us shortly. Okay, let me share screen. So today we are going to do multiplication and division in assembly. I posted the code on the assignment page so you can take a look at it closer. And so let's go through and talk about the lab requirement, and then kind of give you an explanation on how we're going to approach solving this problem in assembly, and then go through the code, and then we will take a look at how we can build our program or assemble our program and then run our program. So it's not too difficult of a lab. We just got to understand the required components and then to be able to implement the solution with that. So the problem statement it gives you is that you have two integers, x and y, and we want to take that and find a product, which is we are going to multiply x with y. We're also going to take it to divide. So we're going to find the quotient of x divided by y. So we would do a division, and then we would do a modulus X mod Y. So modulus, as you know, it is a division, but our result is going to be a remainder. So we want to be able to output the value as a remainder for mod. So your input value is going to be X and Y. And keep that in mind that we are going to use location hex 3100 and 3101 for X and Y. So this is where you set the values, okay? You have to set the values for this one. So after you assemble the program, before you run it, you gotta make sure you go to these locations to input the value you want to test. And then for our program, we need to output the result for the product of X, Y, the quotient of X divided by Y, the modulus of result, or the result for X mod Y. And then these are going to be at 3102, 3103, and 3104 location. So this is where you're going to see the result for the multiplication, the division, and the mod. And then we also want to do input validation. So if X and Y inputs are invalid, in the case that if I set 0 for Y, right, that's illegal to operate because you cannot divide by 0. Then I want to make sure that I check it. So we have to apply some kind of mechanism for input validation. And we want to also use location 303 and 304 for input validation. So in this one, we are going to implement subroutines. And subroutines are functions or equivalent to functions that you see in C++. So here is where we would be able to write out a function, and we will be able to use that function by calling it. So we are going to use JSR. So when you call a function, you would use the instruction JSR to call the function. So that means that we can reuse the function, right, in separate calls. So functions are really meant to handle tasks. And if we need that task to complete multiple times, then we can recall the function. And so we'll expand a little bit more later on in our lecture about functions or subroutines in assembly. And we can also pass values or parameters in our functions, as you know this in C, C++, Java, and Python, right? We can test it by passing the values, or if we need to, pass other form of parameters, we can apply that. So we will work on this. So the example here is we have a function 2n plus 3, right? N is at location 3120, f of n is at 3121. So in this, in order to pass the parameter for n, we would use a register. And in this case, we're using register 0. And register 1 is used to pass the return value for f of n. So you would use one register to pass the parameter for the variable n, and you would use another register, a different register, to pass the return value for f of n. And so from the subroutine, when you're calling your subroutine, right, you got to make sure that these registers are going to be handling the parameters. So here is when you do this execution. So you simply do a JSR, which stands for jump to subroutine. And this is when we call the function. In C, you normally see this in the me, right? But in assembly, you want to place it where you want to call your function. Okay, and so we'll take a look at the listing 5.1 shortly. So when you use JSR, what it does is it's going to take the return address and it's going to tie that address to register 7, okay? So register 7 is a register that's going to work with jump to subroutine, right? And then some of the trap. So you're going to, when you simulate, you're going to see that register 7 is the register that's usually, handling this. So it's really important that you think about specific register that you want to use. So if I'm planning to use register 7, I just got to keep in mind that it's being used for jump to subroutine and other area. And so when you do an RTE, which is a return, when you do that, it's going to terminate the execution, just like remember how you do return 0 in C++. So, or you can return a value from a function. So you return from subroutine instruction, which is an RTE or RET, I'm sorry. And that also uses register 7. It's going to assign the return value to register 7 to the program counter. So this is how it's going to bring the return value to that part of your program. So in this example, or in this particular lab, you are going to have 2 functions or 2 subroutines, mult for multiplication and div for division. Okay. So in this listing, what we're doing is we're looking at the example. If we're doing f of n is 2 times n plus 3. First, remember, just like before, we need to bring in our variable n or our label n. So in this case, I'm going to load n to register 0. And then after that, I'm going to do a jump to subroutine f. Okay. And this is when we call the function f. Then I'm going to store register 1 to f of n, because after I operate the function, right, I would have some kind of value in my register 1, and I want to write that to memory so I can see my result for 2 times n plus 3. And then I halt. Then for your n, we're going to fill it at the location f of n. We already talked about the subsequent location. Now to define the function, you clear your register, right? So here I'm using register 1. So we are going to clear register 1. Then we're going to initialize, we take register 0 and we add it with 0, right? So we have a copy of the value in register 0 to register 1. So basically it's going to copy the n to register 1. The reason why we're doing this is because we're trying to represent f of n, and we already have n at register 0. So we're going to copy that value for n into register 1, which is f of n. And then we're going to take that, we're going to multiply itself. Why? It's because we're trying to represent 2 times n, which is n plus n, right? We already have the n in register 1 after we copy. Now we're going to take it and add itself. So that's going to be 2n. So at this line, right, add R1, 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 we have 2n at register 1. And then after that, I just need to handle the rest of my equation, which is going to take 3, and we're going to add it to 2n. So I know that 2n, where I left last, is at register 1. So I'm going to take that, I'm going to add it with a hex 3. So I have the complete equation. So once I have that for my function or my subroutine, I would then return from my function. So I do an RET and then I do a .n. And that's how you can define a function to be able to apply, right? 2n plus 3, right, as part of your subroutine. So that equation. So here gives you a table to kind of show you how JSR works. Okay. So when you call a function or when you do a jump to subroutine, what it's going to do is going to take the address and it's going to do a +1, because the PC counter, remember that it has to add the 1 to increment it for the next one in line. So it's going to do a +1 with the address. Okay. And then it's based on the address, it's going to know exactly where that function is. So at that point, right, the IR is going to be able to operate and look at the content of the function, which is your function F here. Okay. And then my register 7 at that point is going to be nothing, 0. Okay. Then it's going to move to the second step. So once I have that, my address is already at the PC at JSR. The address is going to be a +1 already in my PC, and I already have the IR. So the next step for step 2 is the only change between step 1 and step 2 for the next step is going to be that it's going to take the address of that function or the subroutine +1 from the PC, and it's going to copy it to register 7. So copy PC to register 7 for the return instruction. And then for the step 3, so once register 7 has the address +1, then the program counter is going to have the address of the function itself. This is where it's going to read your code right here, right? And then your IR is going to be, it has the jump to subroutine for F. So it copied the F address from the IR to the PC. This is where it's going to execute, and then it's going to proceed. So the JSR address +1, it's going to be able to go to the next line after it does the return. So once it does the return from the function, it's going to continue with the rest of the program. Okay. So one of the things I want to address in this particular explanation is I want to talk about saving and restoring. You need to do this for your project, but most importantly, you need to save and restore when your values are going to be destroyed. Meaning that somewhere in your program, in the case where you use it in subroutine, or in the case that your values can be modified or destroyed throughout your program, you need to save it and then later on bring it back. Okay, so when we say save is where we store it to a location in memory for later use, and then we would restore it by going back to it and load from it. So you do a store and load. Okay, so when you save, you're going to store it to a memory location, and we can give it a name like this. Okay, so we store register 5 values to save reg 5, and then we can fill it with hex 0. So what it will do is it's going to take whatever is in register 5, and it's going to put it to the location name save reg 5. And we do this temporarily, right? And then later on in our program, we're going to load from there. So we're going to load register 5 with whatever we see. So in the case where, let's say if I do recursive function, whenever I return the value, I can save it and then later go back and load it so that way I can use it for other things. Doing it this way allows you to consistently have the values to work with, so that way there's not time that you are going to lose that value. Okay, because if you don't do this, what's going to happen is, it might have inconsistent value, or it might not be able to retrieve the value if the value has been destroyed or written over by other processes. Okay, so this is where you want to save and restore, especially when you're using RET or return from a subroutine. Okay, any question? Okay, so by practice, we normally use register 5 and 6 for this. Okay, you don't have to, but it's just the way that we utilize what's shown in the example. So if you continue to use 5 and 6, that's great. If you have other register in mind when you save and restore, that's fine. You just gotta make sure that you use comment or some way to kind of let other people know who reads your code that you are, using some of the register as temporary storage to be able to access temporary storage for your functions or your subroutine. Okay, so our program outline kind of look like this. We're gonna call the molt function or jump to subroutine molt. And with that, we have to define what that is. Same thing with div, right? We have and you normally do the jump to subroutine at the beginning. Unlike C or C++, you do that in main, which is usually on the bottom. We want to handle that at the beginning. And then whatever the return value is, we want to be able to write it to our result address location. So you're going to jump to subroutine for both and then help, and then define your function, right? So think of this as like a prototyping and calling your function at the beginning, okay? So in C++, we more normally prototype and then we define the function later on, and then we call it in the main, but you have to jump to subroutine when is needed. So at the location that you need, and normally we handle that at the beginning. Okay, so let's talk about multiplication. Multiplication, as shown here, is we have x times y. All that is we're going to add x as many times as y. So if I have 5x, I would do x plus x plus x plus x plus x. So I add the x 5 times. And with that, we can loop, right? We can simply loop y times, okay? So the pseudocode for this is here. And this is important because this is what we're going to implement in our program today. Remember that if we're using sign value, a negative value, because you can take a negative times a positive, you're going to have a negative output. So we would do a sign. We want to have a sign of the product, and we need to add 1 to that. So some way to represent a negative value. And if x is less than 0, then you want to convert the x to the positive. So we want to treat it like what you've seen before with the absolute value, but you have to find ways to really represent the negative x. So first you have to have the positive x is going to be negative here. So if x is negative, we have to represent it this way. As a positive, then we're going to sign it. Okay. So a sign is going to be a negative sign. And remember that is a special bit that we put in the front in binary to represent the sign. If y is less than 0, if y is negative, again, we want to convert y to a positive, and then we're going to sign the y. So you're going to treat it like a positive value with a sign. Same thing like x. And then in the case that if we have a 0, then our product will be 0, but y cannot be 0, right? X can be 0 because later on we're going to have the division. So here our product, we would initialize it as 0. And we would implement the while with the nested if. While y cannot be 0, so here's where you want to branch, okay, and check for 0. We're going to do product is product plus x because, if I have 5x, then that means that I can take 3x plus x and x, which gives me 5x. If I have 5x and I have 4x already found through the loop, then I can have 4x plus x. So this is the point on when they say the product is product plus y plus x. And if you think of it this way, we can also optimize this through variable reassignment, right, from a higher level. So we are saying that product is product plus X, Y is Y minus 1 as we implement this loop. If the sign is less than 0, then your product is a negative product. So if we're saying that if it is signed, if it's less than 0, and so here we can check for 0. So we can make the adjustment to be able to handle negative value. Okay, so this listing is important because that's what we're going to use as part of your algorithm in the program. Let's talk about the division now. So we will have X is X divided by Y, right? And then when we handle the mod, it's going to be X mod Y. Okay. So for the division, what we want is we want to first find the quotient. So if I take 12 divided by 6, my quotient is going to be 2, right? But if I take 13 divided by 6, my quotient is still 2, but I have a remainder is 1. Okay, so anytime that you have the X is an odd number, you're going to have a quotient plus a mod value. If my X is an even number, I would have just a quotient, and my modulus result is 0 because I don't have a remainder. So this is why it's stated this way, is that you do have a quotient plus possible an output for the modulus if it has a remainder. Okay, so in this example, we would use X is 41 and Y is 7. So if, in my CIS11 class, I addressed this in how we would break this down into subcomponent. 41 is 5 times 7 plus 6, right? So we can take a look at how this can operate with the multiplication plus a value. Or you can look at it as a quotient plus the remainder to be fulfilling an odd value like 41. Okay. So the way that we design for the division is that the X parameter is passed to the div function or subroutine through register 0. You saw this example earlier, right? And the Y is through register 1. So what we have is that we would say that X can be 0, but Y has to be greater than 0, or if it's negative, it has to be a positive as with sign extended. Okay. And we want to check this to make sure that if it is not, then it's going to return another register as 0, indicated that the result is not valid. We have to do input validation. Y cannot be 0. If it is satisfied that our register 2 is going to have a 1, and the overflow condition cannot be checked at this time. Okay. So here I give you a table. Register 0 is X. Register 1 is Y. Register 2 is the result to check to see if XY is 0. Okay. Register 2 is going to show a 1 if Y is valid, and 0 if Y is invalid. Okay. And so for the division, this is our pseudocode. We would initialize quotient at 0 and remainder at 0. We want to use a register to check whether it's valid or not. We just talked about that for register 2. If X is less than 0 or Y is less than or equal to 0, then exit. And then show valid. For the temp, we're going to use the temp location to hold the number of X's left, because when you do division, simply it's a way that we can subtract X, Y times, right? And so with that, similar to what you see with the multiplication, we would we would implement the do while loop. So we would have while temp is greater or equal to y, we're going to do temp is temp minus y. It's because it's x minus y to divide. So we just keep subtracting y times. That's basically what we're showing. And your quotient is going to be quotient plus 1. Remember that because we need to move down one level, so we have quotient is quotient plus 1. That's what we see with the multiplication, and your remainder is going to be in the 10. So when you divide, you can handle quotient and remainder. And we need to also check for input validation at the same time. So for this, make sure we implement the listing in our program. I want you to set your input for your program, right? Remember that I'm giving you this in decimal in decimal so you can convert it to hex to convert when you set your value with your simulator. And I need you to address these questions. What are some of the key points that you learned by doing this lab? What are some of the challenges that you come across in this lab? How can you apply subroutines in future programming activities? We will have subroutines from now until the end of our lab sessions. And then you will be required to write subroutines in your project. So we have to know how to create functions in LC-3. Okay, any question? All right, so let me go back. So I have this in Word, but you can refer to the image line by line so you can take a look. Okay, so at the beginning, I simply just comment my program objective. I have my lab. This was lab 7. Before last year, there was a holiday, so I moved it to lab 8. But for you guys, it's lab 7. We're going to do subroutines with multiplication, division, and modulus. So we need to represent x and y as what you see as variables. So we are going to load, and you can do LD here, but I chose to do LDI. So we would do LDI x to register 1 and y to register 2. So we would have x loaded to register 1 and y to register 2. And yes, you can clear it right before. And at this point, I want to use the function. So I would do jump to subroutine mult. We want to take x, multiply it by y. So multiplication subroutine there. And then I want to store it out. So we would, my result is going to come from register 3, and you're going to see this at the later part of our program. So whatever the register that we're returning from, we're going to store it to XY. So this is the location where we'll see the product. And then we would say product of XY is stored from R3. Okay, and then after that, we would call the function or jump to subroutine div for the division. You must do this, otherwise you're going to lose your values. So we want to have the product output, and then we would take x divided by y. So we call the function here. And as the result for the operation of that function, we would have a quotient and a remainder. Okay. Now, if the simulator or the editor gives you a hard time with the R, sometimes it does, you can just type it out as a remainder like that, okay? Because sometimes it gets it mixed up with like register, but the point in this is to use some kind of label. So after I divide, I wanted to store quotient value is stored from R5 to quote. And then I want to store the remainder value is stored from R3 to R. And then I halt. So this section allows us to load the labels for XY, then multiply XY, output the product to XY location, call the function or jump to subroutine div to operate the division, output the quotient and its or remainder, or quotient with or without remainder at the location, and then terminate. Now, since we have the function, we have to define them. Okay, and that's the next section. So like what you've seen in the listing that's shown, I want to save register 5. So we would save whatever that's in register 5 to save rec 5. And I would do the same thing to register 6. Okay. Anytime that your values can be destroyed, we want to save to the register. Okay. Now, some people, they do this before the function and then reuse it for multiple functions. The purpose of doing this here is because when I do the division, it's the different values. So I want to make sure that I save it for the multiplication. So as you recall from the top, my Y is in register 2. So here, what I did was I took Y, which is in register 2, and I copy it to register 4. So Y is in register 4. And I want to invert it and make it a 2's complement, right, to represent negative Y. Why don't I just use register 2 is because I have a positive Y and I have a negative Y. So I have to find ways to use the register to keep the Y positive and then make it a negative Y. What am I doing here is if you look back into this area, right? You notice that there's a section where we have to implement the condition for Y when Y is less than 0. So what I'm doing is I'm setting it up to fulfill these conditions or set up the conditions in my code for Y is less than 0 and then also X is less than 0. Okay? So that's being handled here. This is where we have the negative Y at R4. And then what we're going to do is it's going to use register 4 here to check for the branching here. Remember that I'm trying to determine, right, Y is positive or negative. So for the negative value, it's going to then become positive. So if you look at the listing right below it, it's going to say convert Y to positive where Y is negative Y, and then we're going to sign extend it. That means that we're going to use something to represent the sign for Y. Okay. And then so that's what we need to do here. So in the next part of the code, it's going to branch for positive. And so for the negative values, that's going to become positive. So here, what we're going to do is whatever's in R4, it's going to check for P because positive, and we're going to send it to pass loop. And so that means that we're going to need a negative counter instead. That means that we're going to decrease instead of increase. Okay, so we're going to decrease in pause loop. So for the loop, what we're going to do is we are going to check if n is greater than 0, then we're going to make it quit. Then or else we're going to keep going. So here we're going to take R6 and R5, R5 and R4. We're going to add them together. Okay. And it's going to put the result in R6. The reason why I'm using these registers earlier, I have it saved, I have it stored, right? So before that, what I need to do is for the loop, I need to use them to really represent how it's going to multiply. So my R5 and R4, you know that it's already Y, right? And then for the R5, that's going to be my counter. So I'm going to take my counter, add it with that. So we want to check to see if n is greater than 0, where R6 is the output from that addition. So it's going to check if it's 0 or positive, it's going to send it to quit. Then for my R5, I'm going to then add 1. And it's going to keep multiplying until it hits 0. So as long as, because when we decrease, it's going to be, when it gets to 0, it's going to quit. Okay. So R5 plus 1. And then for the R3, this is going to be added with my R1. And so if you look back, right, R1 was X. Okay. In R3, when we store it, you would see that it's XY. So as I would take X, right, because it's product plus X is going to be output product. So what does that mean? When you look at this line, right, we talked about like, oh, how that can represent reassignment. So this is the section that we're doing. We initialize product at 0 while Y is not equal to 0. So the product is product plus X. Remember we talked about if I want to do 5X, it's 4X plus X. So that's what we're doing here is we would take XY plus X. So that's why you would see it like this. It's going to be XY plus X. Okay, and we would put it on XY. So product is product plus X. And then we would force branch it back to loop. And then since we have it quit 1 here, quit 1 is when we're going to return. So back to calling the program. So for the pause loop, what we do here is we are going to copy R4 to R4. So you add 0 to itself. And then we implement the second loop. So same as the top, it's going to be the same thing, but with the quit 2. Okay. So in this case, what we're going to do is we are going to have a loop 2 where loop 2 is going to handle the negative. Okay. So R6, so the same thing as before, same thing with the loop 1 is that you're going to have your Y, right, with your counter and then put it on R6. When it hits 0, it's going to return, which is going to be quit 2. Okay. But I'm sorry, in quit 2, we are actually going to do the 2's complement to handle the negative for the second loop. Now for the R5 here, we're going to add 1 So it's going to be the end of the negative because it had the negative value in. So this is how we're going to be able to handle the negative output compared to the last one. Okay. So it has the negative ends where we would have x plus x times y, put it on xy. Okay. And then we would branch it for loop 2, very similar to the last. And then for the quit 3, we're going to have it negative after it multiplies. So we have to 2 complement it to really show that it is a negative value, right? Because I can have x as a negative value and y is positive, or I can have y is a positive value, y is a negative value, and then x is a positive. So I have to handle it this way. So as we store from earlier, now we're going to load, right? So you put it onto a memory location, and you're going to go and you're going to take it and bring it back to the register. So when you restore is when you go to the memory location and load 5 and 6. Okay. And so with that, what's going to do is going to return, because if you don't, when you send it through the loop, it's going to lose the value. So we want to make sure that we store it so that way each time it's going to be able to produce some kind of output and keep it safe. Otherwise, we're going to lose it. Okay. Any question? Okay, so that takes care of your multiplication, right? And we are using some of the loop for the other. So here's your division. You check y is 0, so you add 0 to it, and then it's going to go here to check. If it's 0, it's going to do quit 3. Then we're going to copy y from register 2, which is the original input, to register 6. We're going to clear register 5. We used register 5 earlier, so we need to clear here. We copy x from register 1 from the beginning to register 3. And we copy y from the beginning from register 2 to register 4 by adding 0. Then now we need to handle the negative y. So we're going to choose complement register 4 after we copy it. So y is in register 4. And we need to do the 2's complement. And as division is about subtraction, right? So you have the negative y already, then you add it to register 3, which is your quotient. So you would have subtract y to the quotient and then put it on register 0. It's going to go to register 0 to check for the negative value. If it is negative, it's going to send it to quit 2, which we defined earlier also for multiplication. And in the quit 2, so some of this is that you would see that we handle this part. Okay. So you clear register, you check for XY, right? And then you make sure that it's in the temp location and you handle quotient plus 1, and then the remainder. So the rest of this is to implement this. Okay. So for the next part, we're going to do a loop. We're going to add 1 to R5 for our counter. And we already talked about how we choose complement the y. So we are going to take x, we're going to subtract y and put it on R3. And as long as it's positive, it's going to keep looping. So it's going to keep dividing. And then when it is 0, when it hits the last part, so after it finished the last loop, it's going to get to 0, which is from register 3. Then it is going to return. Okay. Now this is where we would do the sign value. So I would have register 6 add with register 3. So it's going to add the negative the result to the positive y. And then we need to subtract the counter to represent the sign. So here is where you add the -1 to the counter to represent the sign y. And then we would branch back to quick 3, which is the return. So on the last part, we just need to fill the location that we use. So this is the data. So your input is at 3100. Your second input for y is at 3101. Your product, xy, is at 3102. Quotient is at 3103. Your remainder is at 3104. And for the safe register, you can place this before the others, that's fine, or at the end. You want to use it at hex 0. You don't need a specific location as this is a 10. So we just allocate, right, like hex 0 for it. It eventually goes away anyway. We only use it for save and restore, and then .n. Okay, any question? No question? Okay, so once we have the program written, right, and I'm using Windows Simulator, you're going to build it. So click ASM, and that puts it through the assembler. And then you go and you open your, sorry, 1 second, let me go back to here. My editor. Oops, my simulator, I meant. And then load your program. So if you're using online simulator, you gotta like copy and paste it, assemble it on there, and then you have to set the value. So I'm gonna go ahead and open my folder. To So before I run my program, I need to go to these location. I'm sorry, 3100 and 3101 to set my X and Y, right? And for your assignment, right, we can test it with this one, 10 and 7. So I'll do that with you. So once I load my program, I don't want to run it yet. I want to set the value. So you click on this. Now, if you use the online simulator, you just click on the location, right? Search for the hex 3100. So I am going to use 3100 and 3101. So hex 3100, and then I can set X. I think we set that was a 10 and a 7, right? Yeah. So I can use hex A for X, and then 3101, I would use hex 7. So once I set my value, I'll go ahead and run my program. And then I need to do a jump to see my output. Okay. So here I have my set value for X, and then Y, and then my product. Remember that hexadecimal, right? And then my quotient, and then my remainder. So if I take 10 divided by 7, I get 1 time with the 3 remainder. So it's right. Okay. Any question? So you need to set your values, okay, and then make sure that you do that before you run your program. After you assemble your program, you need to set your values. So I like for you to just give me one screenshot or two. That's fine. I just want to make sure that you have your program running and it works. And then add the question and answer to your document. You can add it directly onto this document and then type out your answer. That's fine too. Okay. So in this program, what we learn is we learn how to write a function in assembly that is called subroutine. We know how to jump to subroutine. We're able to use multiple location to store our product, quotient, and remainder to handle multiplication and division. We also check for X, Y, positive and negative. And when it's negative, we want to handle it a certain way. And you can test it with a negative value, right? So convert your negative to hexadecimal and then set it in there and see how it's going to output. So you can find product, right? If X is negative and Y is positive, is it outputting the same thing? So we can check the mechanism in that to see if it's accurate. As I mentioned many times before, the program is as accurate as its programmer. So you want to look at the input in different ways to kind of determine if your program is good. Okay, because if you only test it one time with positive or test it with a certain value, you also should test it to the maximum capability on the storage to see if it's holding like a certain large numbers. Okay. So ultimately, we are able to use function to operate multiplication, division, or subroutine for LC3 or assembly. And so this is expected of you also in the higher level too. So when you think about writing your program in C, Java, whatever, you should be able to do this. And it might be a lot easier in C because you have a lot more practice. But in assembly, once we get a hang of this, it's going to be pretty easy. We will do another multiplication program by doing bit shift. So it's slightly different than this. But once you do this type of program, you're going to get a hang of how we're going to be able to handle multiplication, adding so many times, subtracting so many times. Okay. Any question?
Can you test negative Y? Because mine is showing a positive instead of the negative.
Okay, so let's look at this part right here. Oh, sorry. I just lost it. Why cannot be 0? Product is product. Oh, that's the small. Okay. For 10, subtract quotient, remainder 10. You test it for multiplication and division?
Yeah.
Oh, yeah, and then you run it and you said that the division shows positive or both
No,
shows positive?
no, the product for multiplication, it doesn't show, it shows the positive version of the what it's supposed to get. No, it doesn't not it, I guess. I don't know what happened. I don't know what's going on.
Okay. I just want to check. Okay. 11 and 12. Let's do that. So for decimal negative 12, my hex is F4. And then for 11, I'll just do hex B. So I'll keep the calculator on. So Let me reload the program. So 3100. And then on this one, I did 11 divided by -12, right? So XB for X, and then hex F for Y. One, two. Wait, okay. Oh, I see. Because I have this is less than this, X divided by Y, I get a 0. And it's not controlling overflow. So for this one, it's 0 out. Right. Let me double check again. It's in there initialized. Sorry. Stop. Yeah, that looks more like it. Mine shows it traps at F5.
Shouldn't
So
your hex 3101 be FFF 3S and a 4 at the end?
301.
Yeah, shouldn't it be 3S and then the 4? If it's
It's
if it's just
only
F,
gonna fit 5 bits for there. Let me see. So F, what was it? We set 31 is B and F4, right? So B divided by on the word size it's gonna show 0. So that's right. Because it's not gonna fit. It's overflowing. So yeah, so even if you check it on the calculator, so for the product, let's check the product. So that's gonna be B times F4. Hold on, let me reset my side on the word. B times F4. Yep, A7C. And then
but that wouldn't be correct, right? The decimal.
what do you mean the decimal?
Well, 11 times -12. Oh, sorry.
You gotta convert it to hex. So if I take hex, I have hex B times F4, right? Which is the -12
Mm-hmm.
is A7C. That's
Mhm.
right. This
Yeah,
is the product is correct.
yeah.
And then for the division, if I take my B divided by F4, I get a 0. That's correct because the rest of this is overflow to the next one, which is your remainder. So let's do this in a size bigger, a double word. Okay, so you can see the overflow. So if I take B, hex B divided by F4, right? It's still gonna show 0 because it's 0 as a quotient. And then whatever the remainder is, it's gonna be an F and what's left from that quotient. So if you take 11 divided by 12, you get a quotient 0 and then that, but because it's sign extended, it's put the F in the front.
Okay.
So
So, but 11 times -12 should be 132, right? Because A7C is not equal to 132 or -132, right?
Okay, so I'm gonna put it back to the word size. So you said 11 times 12 negative, right? Is this.
Yeah.
Okay, on the hex size.
Yeah.
So it's A72. So it's giving you F72.
Oh, okay.
Yeah. Now I fit this onto a word, but what you have is, so when we convert it to hex, it's actually giving you an accurate value for the hex. This is -132, right? And if we take A7C, okay, A7C, right? This is a decimal equivalent.
Oh, okay, okay.
So the way that we treat it, remember that on this is we have to treat it as a positive with a sign extended. Yeah, we will probably, so this one doesn't control overflow. I think that it could do better in that we have to make it a 2 complement and handle the value a certain way. So it's definitely needs improvement for sure. But because in the lab itself, it did talk about like how it doesn't handle the F. The leftover quantity is just the remainder. Where is it? It talks about like it's not able to check overflow conditions not be checked at this time. So yeah, we have some issues with the larger value that's negative.
Yeah, thank you. Appreciate it.
Yeah, no problem. So you're correct, right? It should show the FF and based on this, but we do have this. So if you fully convert it to hexadecimal, it does calculate it correctly.
Yeah, I was only confused because when I put in the calculator, the hex number, I would get such a large decimal number, and I was confused.
Yeah. So just try to use the hex to check it. So we have it right with the hex. Yeah, your calculator, it depends on how you set the size. Sometimes it's, the conversion from the hex to the decimal, it's going to treat like what you've seen before. It's going to add like whatever value and it's going to make it in the 1,000 because it's half all the extra bits. Okay, so we're good here. You can use, but my recommendation for everyone is to take your integers that you're supposed to test, convert it to hexadecimal, And then that way you can see the accuracy in that. And when you check your calculator, use the hex. And you can set this to a word size. That's a 16-bit. That's what we're supposed to use. So for this one, I can do, this is illegal, right? This is going to be invalid because 0 for Y. And then I can make this into a hex. I can make this into a hex, and then I can set the value and check. Okay. If it's large, if it's overflowing, just keep in mind that it's a large value, and you know, there's limitation to your program. So the best thing that you should do is to go through your program and understanding the logic in the program, why we're saving and restoring at a certain point. Why are we reassigning the value and what that means, how we can apply conditions and loops and what the loop should look like, because later on that's expected of you in your project. Okay. All right, any question? Okay, I'm gonna stop recording.